Welcome back to a tutorial on the BJT, and in this tutorial video we're going to discuss about the current components that appear in case of a BJT. Okay, so let's just continue from where we left in the previous tutorial. As a little recap over here, I'd like to mention that in case of the transistors that we just discussed back, BJTs to be specific, as we discussed back in the previous tutorial, that we always needed to keep the emitter base junction, that's the emitter junction, we often call it that way. So we always need to keep the emitter junction forward biased, okay, for operating a BJT in the way it should be, or rather in the way that it is, of course, optimized for operation. Okay, so as you can see, as these two diagrams suggest, for both the PNP and the NPN type of the transistors that you can see over here, that we always need to keep the emitter junction forward biased while just keeping the collector base junction, that's the collector junction, we also refer to it that way, always need to keep the collector junction reverse biased. Okay, so these diagrams suggest the same over here, as you can see. But the polarities, of course, differ in the case of PNP and the NPN type BJTs as well. So if you just imagine that forward biasing as you had seen previously in the tutorials of the PN junction diode, that in order to forward bias the PN junction diode, what we did was that we connected a voltage source across its junctions, or rather across its P and N terminals. Similarly, in order to forward bias the emitter junction, or rather the junction between that of the emitter and the base terminals, we also need to connect a voltage source that way. So there you go. So now we have this particular voltage source denoted with the symbol of V1. That is, of course, forward biasing both the emitter and base junctions of the PNP as well as that of the NPN type transistors over here in the diagrams, as you can see. Okay, so this particular voltage source provides necessary voltage levels in order to keep the emitter terminal of the PNP type of BJT at a higher potential compared to that of its base, while in the case of the NPN type transistor, the V1 voltage source, it is of course manages to keep the base over here comparatively at a higher voltage than the emitter terminal itself. Okay, so now if you care to look at the collector base end of this two transistors over here, you'll also see that in order to reverse bias the collector junction, or rather the junction between that of the collector and the base terminals, you also need to connect a voltage source designated here as V2 in both the cases, okay, with the corresponding polarities, as you can see, in order to keep the collector base junction reverse biased. Okay, so now biasing the junctions in this way, okay, gives rise to certain current components inside the BJTs. So we're going to take a look at them right now. Okay, there we are. Now over here, as you can see that we have a structural diagram of that of a BJT in general, and let's, for example, or rather let's, for your convenience, let's just take it as the PNP type of a BJT. Okay, and if this particular end over here on the left represents the emitter terminal, okay, the one on the right would obviously represent the collector, and the middle one the base. Okay, so now if you all would just care to take a note over here, that since we're basically forward biasing the junction between that of the emitter and the base terminals, which we would just basically refer to as the emitter junction JE, and reverse bias the collector base junction over here, which we would obviously refer to as JC, then in that case we're obviously going to connect the voltage sources, that's V1 and V2 respectively, in somewhat this manner. Okay, so now in order to go forward and study its current components, we have to see, or rather understand over here, that with the forward biasing this emitter junction, okay, now since the this is a PNP type of a BJT, so it's quite obvious that by forward biasing the emitter and the base junction right over here, we're going to basically trigger some sort of current flow between that of the emitter and the base sections of a BJT. So obviously it's quite natural that a current, due to the majority carriers, would just flow over here. Okay, and that way we would just basically call it the emitter current, that's denoted with IE for the majority current carriers, that's the holes over here. Okay, and now also due to the fact that, well, the base will also have, minority carriers, that's the the base would also have the majority carriers of electrons inside itself. And now when electrons under this applied potential over here would also start flowing across the junction, but just in the reverse way. So I'm just going to show that with a different color over here. So the electrons from the base would just flow into that of the emitter. Okay, and that way we would just call it the emitter current, that's IE, the same symbol. Okay, but this is just due to the holes, that's due to the electrons that are just flowing from the base into that of the the emitter section of the BJT itself. Okay, now when the two current components basically, let's just take the whole current component for example. When the whole current component from the emitter just enters into the base, they just enter over there as minority carriers. Okay, and similarly from the base, whenever the electron current component that this constitutes the emitter current over here flows into the emitter section of the BJT, they just enter over there as minority current carriers as well, since this emitter section is p-type material doped. Okay, so now together together both of them would constitute what we would know as the emitter current. Okay, so it's quite natural that an emitter current, due to this sort of a bias voltage, would just flow in this particular direction towards the from the emitter into that of the base section, and that's why the current's direction is, of course, just goes, or rather directed inwards into the emitter of the the PNP type of BJT over here. Okay, so with that said, whenever we would just look at the current components, it's quite natural to also understand the fact that whenever now, since the current component, due to the holes that is flowing from the emitter into the base, will be of a larger magnitude than the current component, emitter current component, due to that of the electrons over here. So I'll just write down over here, that's better. Yeah, so IEP should be greater than that of IEN. It's because the base, as we know, that for each and every type of BJT is always lightly doped. Okay, and the doping concentration being higher in the emitter section would obviously trigger a larger amount of flow of a larger amount of current carriers, that's the holes, from the emitter into that of the base. So now after this whole thing enters, the current components will enter into the base, that's the whole current component I'm just talking about. A fraction of it would just recombine with the available electrons out here and would just go away as a part, and that part would be just referred to as the recombination current. Okay, while the remaining part would just continue its journey crossing the collector junction into the collector section over here. Okay, so apart from that, the emitter current component, due to the electrons, would just originate from the base itself and would just continue its journey into that of the the emitter section. Well, and now that the direction of the electron flow be taken as opposite to that of the current flow over here. So since the holes are flowing this particular direction, that's taken as conventionally as the direction of the current, so it's quite obvious the emitter current, due to the holes in the electrons, would obviously flow in this particular direction. Okay, so now that we have this white color line over here representing the recombination part of the current over here, that a part of the emitter whole current that's just lost due to recombination, due to the available free electrons in the base section of the BJT. Only a part which I'd like to call something like IC1, and that is of course due to the whole current component that's just developing from that of the emitter itself. Okay, so that just comes over here into the collector section of the transistor, while this particular component, let's just call this one, that's the white line I'm referring to over here, it'll just be obtained by deducting the value of IC1 from that of IEP. Okay, so that is better. So that's the component of the recombination current that just enters into the base terminal as a part of the whole current that just comes from the emitter. And now if we just again care to look at the collector base junction once again, then over here we can well see that due to reverse bias of this collector junction over here, it's quite natural that a reverse saturation current would just develop over here. Okay, so a part of in the p-type collector section, the minority carriers are the electrons. So it's quite obvious that the electrons would just try and flow from the collector into the base terminal due to the applied reverse bias. And on the other hand, another current component due to the minority carriers, that's the holes present in the base, would just flow into the into the collector terminal from the base terminal due to the applied reverse bias. Okay, and now that together, okay, I'll just change the color, yeah, and now together they'll constitute the reverse saturation current flowing in the collector section, denoted with the symbol of ICO. And finally what will happen is that this IC1 current component due to the holes, and of course the reverse saturation current component denoted with the symbol of ICO, would just combine, or rather taken together, would give us the total value of the collector current, which should come out of the collector terminal itself. So I'll just call it IC over here. And now also due to the recombination processes, a component of the current would just go into the base over here, as you can see. And also due to I'll just designate them over here. So here we're just designating the reverse saturation current components, so that here the dark blue line would represent the reverse saturation current component due to the electrons that are the minority carriers in the collector, while the lighter purple line over here would represent the reverse saturation current components due to the holes coming from the base terminals itself, where holes are the minority carriers. Okay, so these taken together would obviously give rise to that of the entire base current, which we shall just denote with the symbol of IB. Okay, so here, as you can see, we have the current components of that of a PNP type of BJT, and whenever we shall use an NPN type BJT in place of a PNP type BJT, okay, there you go. So we'll have this sort of diagram for the current components occurring in that of an NPN type transistor as well. Okay, but in the both type of transistors, the main similarity over here being that over here that you can see obviously that the emitter current and the collector and the base currents, they just add up together to give the emitter current. Okay, so I'll just write them down over here so that's easier for you all to understand. So you can see that here emitter current enters into the device, or rather into the PNP type of transistor, and then it just branches out as the base and the collector current. So in that case, the emitter current would be equals to the base current and the collector current taken together. Similarly, in the case of the NPN type transistor, you can see that the collector and the base currents enter together to give rise to the emitter current, which just comes out of the emitter terminal. So in the same way, we have this similarity occurring between both of the PNP and the NPN type transistors. But the only difference between the two being that the current components have a different direction altogether. It's just the opposite in both the types. Okay, now apart from this, we can also see that the collector current IC is of course composed of the factors, that's the reverse saturation current components ICO plus that of the majority carrier collector current component. Okay, that is IC1P. Similarly, we can also see that over here, the collector current comprises of the reverse saturation current component plus that of the majority current carrier component present in the collector. So that is IC1 due to that of the electrons that's represented with IC1N. Okay, and furthermore we can see that the base current component over here well, is comprised of the fact that, well, we have here this part that's just lost in this base terminal due to the recombination, as you can see over here. That is of course given by, well, IEP minus that of IC1P for a PNP type transistor. Okay, and of course over here and another current component, that's the IEN, as you can see. So we just add them up together. Okay, that just makes the base current component for the PNP type transistor, and that for the NPN type transistor, the base current component is obviously, well, given by that of, okay, so sorry there, I just forgot to name it over here. I'll just point them out. Okay, that is just given by, well, IEN minus that of IC1N. Okay, it's a little crampy over here, so I'll just write them down clearly over here. That's IEN minus that of IC1N. Okay, this is the difference between the two current components over here. That's the recombination current component, one of them. And also we got, well, IEP, as you can see over here. Okay, so IEP, that just gives rise to the entire base current component, as you can see over here. Okay, so that done, we can easily understand from over here that, of course, due to the flow of the current components, obviously the carrier concentrations would, well, vary in both the PNP and the NPN type transistors in all their sections. So if you just take a look at the minority carrier concentration profile, first for that of the PNP type transistor, we can well see the yellow lines over here, that's the dotted ones, mark the thermally the minority carrier concentrations in all the three sections under, well, thermally stable conditions. Okay, so you can just see that the in the P type emitter section over here, I'll just write this one as the emitter, that's the base, and here's the collector. Okay, so in the emitter, the electron concentration in the thermally stable condition is denoted with this dotted yellow line over here. But as the the current just start flowing from the emitter into that of the base, and similarly from the base back into the emitter due to the electrons. Okay, we can see that near the emitter junction there is a sharp rise of the electron concentrations that just come in from the base into that of the emitter section, constituting the electron carrier component of the emitter current. Okay, and similarly the holes, whenever they just travel from the emitter into that of the base, they just become, as I said, minority carriers in the n-type base. Okay, so here you can see that since the emitter current has a higher magnitude that of compared to its electron carrier component. Okay, so you can see that due to the hole component of the emitter current, there is a very, very sharp concentration profile existing near that of the emitter junction over here. And this gradually comes down as one goes towards the collector junction over here. Now since this junction is reverse biased, so that's why the concentration drops over here. Due to the reverse bias, the whole current components, that's the holes that just come from the emitter near that of the collector junction, are just quickly drawn away from this junction, and they increase in concentration, as you can see, as one goes deeper into that of the collector section towards the collector terminal, as you can see over here. Okay, and similarly for the NPN type transistor, we also see a similar curves for the minority carrier concentrations in all their three sections, but only difference being that is in case of the NPN type of transistor, the emitter has the holes as their minority carriers, and the the collector also has the holes as its minority carriers, but the base has the electrons, as you can see over here. But the curves remain the same as per the logic provided before. Okay, so with that we just come to the end of this tutorial on the current components of a transistor. So till then we'll just see you back in the next tutorial. So kindly don't forget to watch it, and it's just thanks for watching this video.